In this video, we are going to be looking at solving some calorimetry problems where energy is exchanged between two objects that initially have different temperatures and will ultimately return, or when in contact, reach thermal equilibrium and reach the same temperature. This is usually done through a process or a study known as calorimetry, and I like to remember that in Spanish and other Romance languages, calor means hot. So calorimetry is basically measuring heat, measuring hotness. And it's usually done with, in the two objects, the hot object and the cold object, are usually mixed inside of an insulated container, which is known as a calorimeter. And the purpose of the insulation is to keep all the energy between the two objects. So one object loses energy, all the energy goes to another object. So if you think back to the lab that we used to start this chapter, at one point we had some water and we had a metal, and I think in our case the water was hot and the metal was cold, and we mixed the two of them together so that the water lost energy and the metal gained energy. So they didn't go through any phase changes in this lab. So like water stayed a liquid, the metal stayed a solid, but they both underwent a temperature change, a transfer of thermal energy. So in that lab, water had lost thermal energy, but the metal had gained a similar amount of the same, we assumed, amount of thermal energy. So it's important in calorimetry that we are going to always start calorimetry by assuming that the energy lost by the hot object is the same as the energy gained by the cool object. And I would say that is the fundamentally most important idea in calorimetry. In this first example problem, our ultimate goal is going to be to figure out the heat capacity of brass. We're going to do it in a couple of steps to kind of get you used to the process. So we're going to assume that we had a piece of hot brass that was dropped into 100 grams of water, and we're going to assume that we had 100 grams of each one, so equal masses of each. And we're going to assume that in the lab we measured the temperature changes, so water, and remember we're always concerned with the change in temperature. So the change in temperature for the water was the difference between these two temperatures, which was 1.1 degrees Celsius. The temperature change for the brass was, it's always final minus initial. So the change in temperature for the brass is negative 12.1 degrees Celsius. And that negative really just signifies that the brass temperature went down while the water temperature went up. We also know the heat capacity of water. It's something that you probably have memorized at this point. So we're going to break this down into steps. There's kind of three variables we've been talking about with energy. We've got mass, we've got temperature change, and we've got heat capacity. And energy, thermal energy, depends on all three of those. And so I'm going to start, and I kind of led you to this here with asking you about the water first, but I'm always going to start with the substance that I know all three things for. I know the mass, the temperature change, and the heat capacity. Brass, I only know the mass, and the temperature change, I don't know its heat capacity, so I can't start there. I'm going to start with the water. So the relationship here is that there's 4.18 joules for 1 gram to go up 1 degree Celsius, because I'm assuming this is liquid water. But I don't just have 1 gram, I have 100 grams. And I didn't go up 1 degree Celsius, it went up 1.1 degrees Celsius. So looking at the units here, grams simplify to 1, degrees Celsius simplify to 1, and I'm going to get units of joules, which is good because I'm trying to figure out total amount of energy. So I'm going to multiply all of those, and I get that 460 joules of energy are gained by the water. The next question I'm asked is how much energy was lost by the brass? Well, in calorimetry, we are making this assumption. It is an important assumption. We are going to assume that the brass lost 460 joules because all the energy lost by the brass went to the water. And we're using insulated container, a calorimeter, to try to make that as accurate of an assumption as possible. So we're assuming all energy from the brass went to the water. So that 460 joules is our starting quantity for our second thing. And we're looking for, in this case, heat capacity. Again, the units can really provide us with some clues. The heat capacity is always the number of joules it takes for 1 gram to go up 1 degree Celsius. Well, 460 joules were transferred. However, that was for 100 grams of brass, and the temperature change associated with that was 12.1 degrees Celsius. So to get the joules for just 1 gram, and 1 degree Celsius, it's all really a big ratio. I take 460 divided by 100 divided by 12.1 to get 0.380 joules for 1 gram to go up 1 degree Celsius. And that, if you look it up, actually is right about the heat capacity for brass. All right, this time we have a piece of aluminum being dropped into water, and in this case the water is going to be the thing that's hot and the aluminum is going to start cool. So the water is going to be losing energy and dropping in temperature, while the aluminum is going to be gaining energy and raising in temperature. We don't know in this case what the mass of the aluminum is. That's what we are going to try to figure out. I'm going to start with the water again based on my hint from this problem, but also because of those 3 variables: how much stuff we have, the change in temperature, and the heat capacity. I know all 3 of them for water, where for aluminum I only know the change in temperature and the heat capacity, and I'm trying to figure out the mass. So you start with the thing that you know, all your pieces, all your variables. So our relationship for water is that there's 4.18 joules for 1 gram of water to go up 1 degree Celsius, but in this case we had 100 times as many grams, and the temperature change was 57 minus 62, which is -5 degrees Celsius. You might wonder, like, I'm really not paying much attention to the signs, because at some point the energy lost by one is the same as the energy gained by the water, but just a different direction. One loses, one gains, but the number is the same. So I find it easier to just think about that and not add in the negatives and positives to my work. So 100 times 5 times 4.18, I got 20,090 joules. And we're calculating energy here. We also see that a gram divided by a gram simplifies to 1, a degree Celsius and a degree Celsius simplifies to 1, so the water gained 2,090 joules. The aluminum, since this is calorimetry and we are making a big assumption, we are assuming that all energy gained by the aluminum came from the water. So all of that energy we're hoping went to the aluminum, all those 2,090 joules. So that's our starting point for our second step, 2,090 joules. And the heat capacity, the relationship that applies for aluminum is 0.9 joules for 1 gram and 1 degree Celsius. So we're actually going to divide by the heat capacity because we know how many joules we have to spend, and we want to know, we're looking at how many degrees Celsius we can get and how much mass we can heat up. Also, another way to think about it is that if we've got units of joules on the top, and we're not trying to get units of joules, we're trying to get grams. So our goal is always units are going to be on the top, and our units we're trying to get rid of be on the bottom. So that's another reason I knew. I also know my target mass. My goal is grams, so that needs to be on the top. So when I do this math, 2,090 divided by 0.9, I get 2,322, and the units of this are grams that can be heated up 1 degree Celsius because the joules cancel out. Now, I am not going to just heat up 1 degree Celsius. I want to heat up the temperature change up here. Delta T is 57 minus 21, which is 36 degrees Celsius. So, hey, I don't want just 1 degree Celsius. I want to divide by the number of degrees Celsius I'm actually getting. And also, if you want to think about another way, I want to get rid of units of degrees Celsius, and I need my answer to have units of grams. So if I divide by degrees Celsius, that accomplishes my goal. And when I divide, I got 65 grams, which seems like a reasonable mass since it was 100 grams of water. It doesn't seem like a crazy different mass. So 65 grams of aluminum must have been the mass. In the last example problem that we're going to look at, we're going to consider mercury being dropped into water. This is the most difficult type of calorimetry problem because in this case, the final temperature is what we don't know. That means that we are not able to calculate the change in temperature for either substance. We know both masses and we know both heat capacities, but we do not know the change in temperature. So there's multiple approaches to solving this problem. But what I'm going to do is kind of a comparison, how much energy each one has available for every 1 degree Celsius temperature change. So I'm going to look at water. For water, we've got 100 grams. Sorry, I'm changing the mass of mercury. We've got 100 grams of water, and it's going to require 4.18 joules for 1 gram to go up 1 degree Celsius. So the water has available 418 joules for every 1 degree Celsius temperature change. Mercury, we've got 50 grams of it, and the heat capacity for mercury is 0.140 joules for 1 gram to go up 1 degree Celsius. So we have 7 joules for every 1 degree Celsius temperature change. If I just compare these two numbers for a minute, I know that the amount of joules exchanged has to be the same at the end of the day because this is calorimetry and all the energy lost by the mercury has to go into the water. That has to be true. That's our underlying assumption here. However, I also noticed that this is a lot smaller number. It doesn't take much energy. The cost for 1 degree Celsius is very small for the 50 gram sample of mercury. It takes a lot more energy to get the 100 gram sample of water to change a degree Celsius. So the next thing I'm going to think of is how much greater is the change in temperature for mercury than water? How much greater is the change in temperature going to be? So I'm basically saying if it takes 418 joules for 1 degree Celsius for water, I'm comparing that to the amount of energy it takes for 1 degree of our mercury sample to change. And we're saying, well, how much bigger is this than this? So 418 divided by 7 is basically 60 times more change in temperature for the mercury. The mercury is just going to have a lot bigger temperature change. So if I think about this temperature range that we have, the temperature is going to be somewhere between 150 and 21, somewhere on this scale. But the change that mercury goes through, this has to be 60 times larger. And this change that the water goes through is like 1 time, or like 1/60th. We've got in total like 61 increments, 60 units for what the mercury is going to do, and only to every 1 change in temperature that the water is going to go through. So the difference between 150 and 21 It's 129 degrees Celsius apart. I'm going to take 129 and I'm going to divide it by 60 into 61 parts. And I get 2.1 degrees Celsius is like one temperature change increment. So the water only gets one temperature change increment. So for water, the temperature is going to go from 21 to 23.1 degrees Celsius. The mercury, it's got to have 60 times more temperature change because there's 60 times more energy required for every 1 degree of water change. So mercury started at 150 degrees. It's going to lose 60 times as much temperature as the water gained in temperature. So 150 minus 2.1 times 60 is 24 degrees Celsius. And that's really pretty close to where the water ended up. So that final temperature is going to be somewhere between 23 and 24 degrees Celsius. So we've got a much bigger temperature change for mercury because it has a much smaller heat capacity than water, which is a realization that we came to at the beginning of the year. The last thing I'm going to do is show you one other way to solve this last problem that's more formulaic and not as in line with how we've been solving problems this year. And I want to present you, I don't have time in class, but I want to present you with two different ways to solve the problem so that you can pick the way that's most comfortable for you. So if you're good with this, stick with this and you don't need to watch the rest. If you need another example, check out the next page. If you've been following along all chapter, you have heard me saying over and over again that the amount of thermal energy in an object depends on three things. It depends on its mass, it depends on the heat capacity, which we can just abbreviate C for capacity, and it depends on the temperature change. And that heat capacity incorporates the fact that something's solid, liquid, or gas, and also it incorporates what type of substance it is. So we've been doing this on every calculation, just not thinking about it like a formula. We've always multiplied the heat capacity times the temperature change and times the mass to get an amount of energy. We also know that in this problem, the energy from the gained by the water is equal to the energy lost by the mercury. So we can write a little equation that says that the energy, the mass, heat capacity, and change in temperature for water is equal to the mass times heat capacity times change in temperature for mercury. And we're going to plug in all the things that we know into this formula of sorts. The mass of water is 100 grams. The heat capacity of water is 4.18 joules for every 1 degree Celsius. The change in temperature we don't know, but I do know that change in temperature is final temperature minus initial temperature. I don't know the final temperature, so we're just going to call that X, or you can call it TF if you like. And the initial temperature is 21 degrees Celsius for the water that was just given to me. And on the other side, this is the energy of the mercury. So we got the mass of the mercury, which is 50 grams. And we've got the heat capacity of the mercury, which is 0.140. And then we have the temperature change of the mercury. And the mercury, again, we're going to call the final temperature X. The initial temperature is 150, so X minus 150. One more thing that we're going to do, since we're doing this more of an algebraic way and I can't think my way through it, I'm going to add a negative sign here. And that negative sign is there because mercury loses the energy. So we put that negative there to signify losing energy. But we're going to have a positive over here because water gains energy. Now this was really done the thoughtful part of this, but the algebra in this method can get a little messy. So first I'm going to multiply the things in the front. So 100 times 4.18 is 418. X minus 21. On the other side, we've got 50 times 0.14, which is negative 7. Hey, that looks actually just like the numbers that we got when we solved the problem the other way. Now we're going to do some distributing. So 418x minus 21 times 418, which is 8,778. And on the other side, negative 7x plus 7 times 150, which is 1,050. Now I'm going to collect all the x's, all the x terms on one side, and I'm going to collect all the constants on the other side. So add 7x, and that gets me 425x. And then I'm going to add 8,778. So 8,778 plus 1,050, I get 9,828. And the last algebraic step is to solve for x by dividing by 425. So I'm going to take 9,828 divided by 425, and I got 23.1. I got to remind myself that x meant, the way I defined it in this problem, x was the final temperature. And notice, this is the exact same final temperature that I got with the other method of calculation. So you can do this either way, but both the mercury and the water are going to end up with a final temperature of 23.1 degrees Celsius.